Hello everyone and welcome to my quick tutorial on TripleK package for Mathematica. If you know what TripleK integrals are and you are just interested in the package, just skip to this time. And if you want to learn what TripleK integrals can do for you, stick around. Okay, so what TripleK integrals do is they express a large class of Feynman integrals and conformal three-point functions, and they provide exact analytic results that were previously not known. And this is implemented by a reduction algorithm that was presented in this paper. And it's very convenient for cosmology. Why is it convenient for cosmology? Well, this is because in holographic cosmology, we would like to calculate holographic correlation functions, something like this, and using some sort of DSCFT or ADS-CFT, we relate these correlators to correlation functions in the dual field theory. And if we are talking about real universe, then these guys are correlation functions of stress tensor in three-dimensional quantum field theory. Now, how to relate these things, that was worked out for the first time probably in this paper by Juan Maldacena. And if we go to page 31, we find these kind of formulas. So this is a general ansatz that will appear no matter which version of the correspondence you use. The cosmological correlators will be related to correlation functions in the dual field theory. Now, if we use some specific realization, such as this one, which is worked out in a series of papers, basically starting from this one. So the power spectrum and two-point functions of transverse traceless gravitons are expressed in terms of these A and B coefficients here. So these guys are given by a two-point function of the stress tensor. In general, the two-point function of stress tensor is transverse, so you can decompose it into two pieces. The first piece is traceless, so this tensor here is traceless, and its coefficient is A, and then this part is full trace, and its coefficient is B, and so B is related to the two-point function of zeta, and A is related to the two-point function of gamma. The same story happens for three-point functions, and I have here the results. So all kinds of three-point function of scalar and tensor perturbations are expressed in terms of three-point functions of stress tensor. And so we want to evaluate these kind of three-point functions on the right-hand side. And as one can expect, this may be difficult. So what are the examples that we want to consider? So basically, the two main examples is okay. So let's take a dual field theory to be just a free theory, and so then when we want to evaluate things like three-point function of stress tensor, we have to basically, so in free theories we just need to calculate like 3 points, one loop integrals in d equals 3 spacetime dimensions. But probably more interestingly, we could say, okay, let's start with some CFT, like a free theory, and we can deform it by some scalar operator. So if we start with free theory, we can take classically marginal operators such as 5 to the 6, or some generic nearly marginal operator O of dimension 3 minus lambda. And so in this case, to use the correspondence, we will have to calculate three-point functions such as this, let's say. So now we can see that, okay, if T mu nu is the stress tensor of a free theory, this will be some horrible multi-loop multi-loop Feynman integral. And if we just, instead of 5 to 6, put some generic operator, then we have to know what is the most general conformal structure of this 2-point function. And the last remark is that in all these cases, what can happen is that these correlation functions have some singularities. If this happens, the singularities must be cured by renormalization. And when the renormalization is required, many of these naive relations, like these ones, they can fail. And so one needs to be very careful in such cases. Okay, so this sounds like a difficult problem. Can we deal with it? And it turns out that yes, and this is exactly what the TripleK package offers you. It delivers tools for calculations of all these 2-point functions. And now I will show you how to do it. So what are TripleK integrals? Well, it's very easy. A TripleK integral is an integral that contains 3 Bessel K functions, or the Bessel functions of the third kind, and is given by this integral. It depends on 3 parameters that will basically have an interpretation of magnitudes of 3 momenta that satisfy momentum conservation. So these guys appear here and also as arguments of these 3 Bessel K integrals. And then there is a 4 parameters, a single one called alpha and 3 parameters called beta. The parameters beta are orders of Bessel K functions, and alpha appears as this power over the integration variable x here. And we know from basic holography that this object is basically a 3-point function in ADS for the simplest Witten diagram that we can write, because the bulk to boundary propagator in momentum space is expressible in terms of Bessel K. So we already know from this that this object indeed represents a 3-point function, scalar 3-point functions, and then these parameters, alpha and beta, are related to dimensions, spacetime dimension and conformal dimension in this fashion. Okay, so it turns out that this is not only true for scalar correlation 3-point functions, which is the same expression written here. It's also true for all kinds of tensorial correlation functions. However, you have to work a little bit harder. So let's say for a 3-point function of a stress tensor and 2 scalar operators, first what you have to do, you have to decompose it into a transverse traceless part that's transverse and traceless with respect to these indices. And then there is some sort of rest, which you can always recover from order entities. So this is completely expressible in terms of 2-point functions. And then you have to deal with this transverse traceless part. It turns out that in any case, the transverse traceless part is also expressible in terms of TripleK integrals. You have to do some sort of decomposition. In this decomposition, you have to deal with the tensor structure, obviously. And then you have some scalar functions of momenta, which we can call form factors. And all these form factors can be expressed in terms of TripleK integrals. A difference between the scalar case and this case is that the indices here may be shifted by integral numbers. And for this reason, instead of this I, which is a TripleK integral, we define a reduced TripleK integral given by J, where we only indicate these shifts, while we assume that values of alpha and betas are fixed according to the dimensions of operators that are considered here. So all of this was worked out in a series of papers, and the first one was this one, implications of conformal invariance in momentum space. And for example, if we go to page 74, we can find all these decompositions for, in this case, 3-point function of stress tensor and 2 conserved currents. And there's a lot of formulas, but so for example here, we see how this 3-point function is given in terms of transverse traceless part, and a lot of stuff here that accounts for all the stuff that's not transverse traceless, but all of this is expressible in terms of some two-point functions. So this is all due to water entities. And then here we can see how the transverse traceless part is expressible in terms of form factors. So in this case, we have 4 form factors: A1, A2, A3. This is also A3 with some parameters, with momenta switched, and A4. And eventually you can solve water entities and you can arrive at this sort of a solution. So all 4 form factors are given in terms of TripleK integrals. And this is a very powerful and novel approach to the problem, because many of these TripleK integrals now can be evaluated explicitly. Another application of TripleK integrals comes from the fact that many 2- and 3-point Feynman integrals can be expressed in terms of TripleK integrals, and these can be evaluated explicitly. So in particular, all these kind of integrals, so this is a 2-point function-like integral. We have 2 factors in the denominator, but with arbitrary powers and some numerator, and also the 3-point function-like integral, where you have 3 factors in the denominator with some arbitrary powers here and some numerator. All of these can be expressed in terms of TripleK integrals. So here we have an example of how it works for just a scalar numerator, and we have TripleK integrals on the right. And so now all these integrals can be reduced to TripleK integrals. And now the question is whether we can evaluate these TripleK integrals explicitly. And indeed, there are many cases where we can do it explicitly. And one of the 2 important cases that we'll use here. So one case is this one. So this is a case where all beta parameters are half integral, and this happens for operators of integral dimension in odd dimensional spacetimes. So in particular in d equals 3, if we have operators of integral dimensions such as stress tensor or conserved currents, all TripleK integrals, and by extension all Feynman diagrams involved, will have will produce explicit expressions. Another case, which is more complicated, but it's also solvable and expressible in terms of elementary functions, basically it boils down to correlation functions of operators of integral dimension in even dimensional spacetimes. If you want to know more about it, please go to this paper. This is a paper that explains in very basic ways the package, TripleK package, and it contains also an introduction with all the references and a short introduction to the story. So let's look at the package. When you open this paper and you scroll down a little bit, you get a link, you click the link, you can download the package. And if you click here, you'll get the package. You unpack whatever is in the package and you find 9 files. These 2 Mathematica packages are the heart of the package. Basically, TripleK contains all the procedures, and the rest are examples and results on various correlation functions. So you can look at these, and these contain much more information than what I'm going to tell you now. Okay, so I saved this notebook in the same folder as the package. So now we can just use the get command to get the package. And the first thing that we will do here is to calculate 2- and 3-point function of the stress tensor, and actually its trace, for the theory of 3 scalars. So here is the stress tensor in momentum space for the theory of 3 massless scalar. This P tensor here is given by this combination. We work in Euclidean signature. And so the 2-point function is given by this expression. So we have these 2 terms. The first part is this prefactor, and then the actual momentum integral. Okay, so first we define this tensor P here, and to do it we use delta. Delta will be recognized as a Euclidean metric. Okay, and now we have this prefactor, so prefactor, and the numerator that's given here. You can also use subscripts instead of brackets, that's equivalent. Okay, so this will be our numerator, and now how do we represent these loop integrals? So these kinds of momentum integrals are represented by loop integral in the package. This is very similar and inspired by package X. So what you have to really care about is the order of these parameters. So this delta 1 and delta 2 are the powers in the propagators here. So for the standard propagators, delta will be equal to 1. And then we have numerator and this the loop momentum. Okay, so let's go back. So we want to consider a loop integral in 3 spacetime dimensions, that's D, and then the powers here are k squared and k minus q squared, so delta 1 and delta 2 are 1 and 1. And then we put the numerator here, so this k is the momentum flowing in the loop, and p is the external momentum. Okay, and now we can just use loop evaluate to evaluate this integral. Okay, and we got this result. And we can check whether this is correct or not. So first we contract with our prefactor. This. And now we can do various checks. So first of all, this should be our 2-point function of stress tensor. So it should be transverse. So if we contract it with external momentum, this should give us 0. And indeed it is 0. And we can also take trace of this expression. And when you take trace, we got this result. And so if we go now to the paper here, we see that indeed the 2-point function of traces is equal to p cubed, in our case, over 64. So this is exactly what we find. And we can also find a and b coefficients given by these formulas. And in this case, we find they are equal and equal to 1 over 256, which is also the correct result. Okay, so this is how we can deal with the 2-point function. Now let's do the 3-point function. So first let's calculate the 3-point function of traces of stress tensor, but let's do the same thing as before. So let's see, this is the integral that we have to do. So the 3-point function is equal to this. So we have these 3 p tensors here, and then this one loop 3-point integral to do. So the same thing, we have the prefactor here, and this numerator here is just written here. So let's execute. Okay, and similarly as before, now we have to write down this loop integral. So it's very similar. So the first argument is the spacetime dimension, and then these 3 powers. And this is very important here. You have to see the order of these guys. So the first parameter, delta 1, is actually the power of k plus p2. This is for symmetry reasons. And then the next one is k minus p1, and then the last one is power of k. So here we have 3 spacetime dimensions, and all powers are 1, these are standard propagators. Then we have the numerator that we wrote here, and we do the loop momentum integral over k. And in the case of 3-point integrals, we do not specify external momenta. It's always assumed that the external momenta are p1, p2, and p3, and they sum to 0. Okay? So we get this integral, and we take our prefactor, and we will, because we will consider here only traces of stress tensor, we trace it. Okay, so now we have to multiply this with this integral and contract all the indices. Well, if we just multiply it and do contract, nothing really happens. And this is because contract doesn't go in the integral. And so there is a function called k-simplify, and if we execute this k-simplify on this expression, then it will indeed go through all these contractions within the integral. Okay, and we got this expression, and now we can just do loop evaluate. And this is the final result. And this result hopefully agrees with this result here. And indeed, we have 1 over 128. And then this stuff should be this stuff. Okay, and our final example will be a 3-point function of a stress tensor and 2 scalar operators. So what we want to do first, we want to calculate the 3-point function in theory of 3 massless scalars, well, this 3-point function basically, here contracted with helicity tensor. So first we calculate just 3-point function and then contract it. So this is how we do it. So we take the same prefactor as we had before, but we only contract now 2 indices. So mu3 and the nu3 remains. These are the 2 indices on the stress tensor that's not contracted. And just to make things slightly faster, I will first just explicitly contract the numerator before substituting to the loop integral. So we just do it here. And now we substitute the loop integral. Here, just to be safe, I put dimension to be 3 minus 2 epsilon. So the final result is finite. The problem is that some intermediate steps may have some divergences. And yeah, this is just for safety. So, okay. And now we do loop evaluate, and the result is obviously long. You can see it, and it will take a moment, but it's worth it. Okay, so we got our result, which is a huge mess. But because we want to contract it with helicity spinors, helicity tensors, the only thing that matters is coefficients of these 2 vectors. So we just kill everything else. And okay, we found this expression. And now when we contract this with helicity tensor, we just basically remove these 2 guys and put this expression where lambda is standard Kähler lambda. So we can get it by using K full expand. So this is what lambda is. Okay, and this expression now should match exactly, well, not exactly, up to a constant. This expression up to a constant because, well, I didn't care about these constants. So let's just check it. These A1, 2, and all the other things are the symmetric polynomials written here. And then this expression is this expression here. And if we divide what we found by what it should be, it is exactly equal up to a constant. Okay, so the next thing that we may want to do is to consider 3-point function of stress tensor and 2 scalar operators of dimension 3. So now, if we consider cosmological correlation functions, where the deforming operator, where we have a CFT deformed by a scalar operator of dimension close to 3, then there is some work involved, but basically what one can show is eventually that the 3-point function that we are looking for has this sort of a prefactor that's because the operator here is not exactly marginal. And then what stands here, so this piece, this is actual 3-point function of the stress tensor and 2 scalar operators of dimension 3. So this is what we will calculate here. First we will calculate it using just general CFT considerations, and then we will also calculate it in theory of 3 massless scalar.
Okay, so if we include the second package that's in the whole package delivered, let's do it. Now we will have access to what we call here primary solutions. So let me explain what it is. So we found before this the composition of the three-point function of stress tensor to scalar operators, and the transverse traceless part contains this form factor A1. And what primary solutions of TOO is exactly the list of all form factors. In this case, there's only one, and how it is expressible in terms of TripleK integrals. And here alpha 1 is a constant. So this tells us that A1 is equal to this integral times alpha 1. So it's exactly what's written here. So let's do it. And because this is the reduced integral, we still have to put dimensions. We can do it by using this function j2i, where this is again the spacetime dimension 3, and these are the dimensions of the three operators. So stress tensor has dimension 3 dimensions, and then two scalar operators also of dimension 3. And so we see that the form factor A1 is given by this TripleK integral times an arbitrary theory-dependent constant. So this is very easy to evaluate. Okay, and we find this expression. And now this expression should match this expression. And this is indeed the case. These are symmetric polynomials in P1, P2, and P3. So when we do symmetric reduction up to a constant, this expression is exactly this expression. And of course, the denominator also matches. So good. So we found the three-point function of the stress tensor at two. Or at least we found transverse traceless part of the three-point function of the stress tensor and two operators of dimension 3 in 3 spacetime dimensions. And now we can check it, or basically evaluate the value of the scheme-dependent the value of the theory-dependent constant in a specific theory. So in our case, 3 massless scalars. So to do it, well, we have to write down the Feynman diagrams. So the Feynman diagram, in this case, we have 2 5 to the 6 operators. This have dimension 3 in d equals 3. So, and then we have insertion of stress tensor here. So what we have to do, we have to do this for loop integrals first, and this will produce some sort of effective propagator. And then with this effective propagator, we will have a single loop with 3 points. So to do it effectively in Mathematica, we can use function fold. So if you don't know what fold does, it has 3 arguments. First argument is the function that we will recursively apply arguments. These will be these arguments, and the starting argument is a. So exactly what you can see here, if I do fold f8345, I get this expression. So now if a is also f12, I get something like this. And now think about these numbers as just being k1, k2, k3, k4, k5. So this is the structure here, and you can write it like this. So you get these nested integrals over k1, k2, k3, and k4. So if we want to calculate this effective propagator, we can now use fold. The starting point, so this a here, will be just this most inner integral. So this is loop integral, e3 minus 2 epsilon dimensions. The standard propagators, numerator is 1. We integrate over k1 as here. And the result depends on k2, which is here. And then we recursively substitute the results to the next loop integral. And here, because we only have one propagator here, so this one, while 0, that there's no other propagator. The other propagator is whatever we get from the previous integral. Okay, and we do it for k equals k1, k2, k3, and k4, and the final k5 will remain for k. Okay, so we get this structure, and we can now evaluate this effective propagator just to see what happens. Okay, and I mean, it always happens that it's just some prefactor, and it's also interesting that this prefactor diverges. You see it's gamma minus 1 plus regulator, and we have k to some power, and notice this is a positive power, not negative power, so this is indeed an effective propagator, not the usual propagator. Okay, and now we substitute this effective propagator into the momentum integral. So our 3-point function looks exactly like this. So we have again our familiar tensor P, and then this loop integral is given explicitly here. So we have our effective propagator, then the two propagators associated with these two lines, and the vertex structure of the stress tensor. So this is exactly what we have here. And now we can evaluate it. As you can see, this expression is actually divergent, but we still didn't apply the tensor P, so let's first do it. And it's also long. Okay, so let's contract it with our tensor P. And as you can see, it's still divergent. Now, is it good or is it bad? Because before we found our form factor and it did not have any divergences. Well, actually it's okay, because what the divergence is multiplied by, this, as you can see, this is a transverse but not traceless tensor. So the divergent terms are not transverse traceless, and in fact you can relate them via word entity to the 2-point function of our scalar operators. And so while this is the full 2-point function, the 2-point function is divergent, and these divergences must be cured. The transverse traceless part, in fact, is finite, and this is what we get here. So there is a trick to get the transverse traceless part. If we remove momentum P2 and use only P1 and P3, and then look for the coefficient of this tensor, then this is proportional to the transverse traceless part or to the form factor A that we had before. And when we take this coefficient, we see that this is finite. So indeed, there is no infinity in the transverse traceless part, although the remainder of the correlation function may be divergent and requires a normalization. And now we can compare it with our previous result, which we stored here. So this is what we found before. And these two results are indeed identical, and we can find the value of alpha 1. As one comment here, this is not actually alpha 1 for the theory of three scalars, because when we do this kind of integrals, there are some symmetry factors because of permutations and such, which we didn't include. But of course, when you count this properly, you can recover the exact value of this alpha 1 or P coefficient by this method. So this wraps up my presentation of TripleK Mathematica package. I hope I convinced you that these horrible calculations are not that horrible after all, and I showed you how you can apply them to holographic cosmology. Please refer to this paper for more information and download my package from this website. Thank you very much for your attention, and have fun.